Fabric is made from thousands of braided threads. This mill has 700 bobbins of polyester. Each bobbin contains 250,000 meters of thread. We begin by separating the threads. This warp unit takes the 700 strands and assembles them. Then this comb separates them. Other strands are added, and in total, there will be 7,000 of them well aligned. One fabric is composed of threads braided at 90 degrees. The warp threads are assembled lengthwise, while the weft threads are joined transversely. To prevent the threads from tearing, they pass through a bin of glue. These rollers eliminate the surplus. The glue will be removed with water before dyeing the threads. The glued together threads exit this machine. These large green cylinders are heated and dry the glue on the threads. Knitting will soon begin. The 700 strands are newly separated on this loom roller. Each thread must pass through a blade to produce a specific design. This machine takes the 7,000 strands of thread one by one, and they pass through the blade. It's a highly precise operation. The threads pass through a blade, and the weaving finally begins. On this Jacquard-type loom roller, the warp thread is inserted by a jet of air. The weaving machine assembles two loom rollers made of 7,000 strands. The fabric reaches a width of 3.65 meters. The dark threads are inserted into the weave. They insert 600 weft strands per minute. The blades remove the weft strands to insert the warp ones between the two. A comb pushes the weft. The plate of the breakage chain stops the machine should a thread break. This bobbin contains 250,000 meters of thread. That's 250 kilometers. The weft thread is in the insertion nozzle. When a weft is inserted, an air jet nudges it in. The loom roller operates at full tilt. It makes 600 thread intersections a minute. Weaving is now over. We move on to the following steps: washing and dyeing. Washing is done in a soapy solution at 80 degrees in a continuous manner at a speed of 60 meters of fabric a minute. The fabric is rinsed in clear water of about 30 degrees. Now it's on to dyeing. This is done with jets. Up to 12,000 meters of fabric are placed in clean water into which colorants have been added. The solution is heated and the fabric soaks here for about 6 hours. Then it will be rinsed in lukewarm water. The fabric is placed in a bin. This machine is called an opener. It unfolds and stretches the material before rolling it up on an immense roller. And now the roll is almost full. We now move to thermosetting in a high-temperature oven which dries the fabric. The temperature is 200 degrees centigrade at the oven's entrance. The fabric circulates here for 45 seconds. This finished roll weighs 1,500 kilos. The bobbin that we saw at the beginning has produced 25 kilometers of fabric.
Lapel pins let you proudly show off where you've been or where you stand. From an event you've attended or your political beliefs to your professional affiliation or your favorite sports team. Lapel pins cost pennies to produce, but some are collector's items worth thousands of dollars. They may be tiny, but they're out there in huge numbers. This one company turns out about 5 million lapel pins a year. It all starts with a sketch of the pin design, and from that, the master, a negative made of magnesium, a type of metal. They'll make copies of this master to create a production mold. But first, using what's called a coping saw, they cut out the front and back pieces of the master. Using a dispenser about the size of a sewing needle, they glue the pieces together with epoxy. It takes 5 minutes to dry. Then they cast enough copies of the master to fill up a rubber disc. After tracing the outlines, a worker uses a surgical knife to meticulously carve out the cavities. He softens the rubber with paint thinner to enable precision cuts. Then he places a copy of the master in each cavity. Another disc goes on top. Then it's into a machine called a vulcanizer for 1 hour. This machine uses heat and pressure to cure the rubber, making it as hard as a car tire. It also melds the rubber around each master copy, embedding the detail. This will be the production mold for producing this pin design. Now, using a surgical knife again for precision, they carve out sprues, channels that during the casting process will direct the flow of molten metal to the cavities. They also make smaller, curved channels called runners to filter out any air or dirt particles. It's crucial to position the sprues and runners correctly because this mold produces an entire line of a particular pin. Mess up and they'd have to remake the mold from scratch. Next, they insert a centimeter-long brass tack called a post into each cavity. It'll later fasten to a clasp, attaching the pin to clothing. The post goes in now rather than later so that it will fuse to the back of the lapel pin during casting. Now to close the mold, they align the buttons on one half with the depressions in the other half. The mold then goes into what's called a spin casting machine. Using a cast iron ladle that can withstand the fiery temperature, they pour in molten metal, either pewter, zinc, or a tin alloy. As the machine spins, centrifugal force propels the metal into every nook and cranny of the cavities. After a minute of spinning, 400 rotations, the mold comes out. The metal takes about 5 minutes to cool and harden. The factory remelts the excess metal for the next batch. Next, a brass clasp called a clutch goes onto the post. Now the lapel pins go for an hour-long wash in soap and water and abrasive stones. The stones smooth out any rough edges. The pins go into the electroplating tank for a surface coating of metal. How many coats and the types of metal vary with the design. An electric current draws the metal particles onto the pins, plating them thoroughly. These pins first get copper plating, then nickel plating, then gold plating. Now it's time to paint the lapel pins. Workers follow a numerical guide like a paint-by-numbers kit. They paint each pin individually using minute quantities of epoxy paint. They control the paint syringe with a foot pedal. Once the paint dries, a machine called a pad printer gathers up ink and stamps on the tiny details, the ones too small to paint by hand. Pierce the post through the fabric, secure it with the clutch, and this lapel pin is now ready to wear. The earliest written record of a kite tells the story of a Chinese general in 206 BC who flew a kite over a wicked emperor's palace. He marked the line to measure the distance, then reeled it in. His small army then dug a tunnel into the palace courtyard, launching a surprise attack that conquered the emperor. To Today's two-line kite, as the name implies, has two lines to pilot it. It can fly nearly 40 meters high. This kite is made mainly of a lightweight nylon fabric that is waterproof and fade-resistant. It's less than 1 millimeter thick, so it's reinforced with nylon mesh to reduce ripping. The kite's other components include nylon and elastic cords and straps, fittings made of leather, rubber, aluminum, and plastic, and carbon rods. The kite maker starts with a pattern made out of pressed wood. She marks out a piece of fabric and, with a few bricks to hold the fabric in place, cuts it diagonally. In sewing terms, that's called cutting on the bias. This will stretch the fabric and help it fly. Next, she cuts more pieces of fabric, this time in a different color. This kite has 8 fabric parts that fit together like a puzzle to create a 2.5-meter wingspan. The kite's left and right sides are mirror images, so there are only 4 different shapes to cut. They range in length from 25 centimeters to 1.2 meters. From start to finish, it takes one worker about 2 hours to make this model called the Dragonfly. First, the kite maker sews the longest part, called the belly, to the other parts. She double stitches with heavy-duty nylon thread to help the kite withstand winds of up to 35 kilometers an hour. She makes tiny incisions along the belly's curved edge so she can fold it and sew in what's called tension line. Tension line is a type of nylon cord she'll sew into all the seams of the kite's lower sections. It'll give the kite some structure and help keep it rigid while airborne. The kite maker secures each line with a knot, which can later be loosened or tightened to adjust the kite's overall tension. The kite maker uses straps made of very durable yet flexible plastic to line the middle and the edges of the wings. The straps strengthen the kite, enabling it to survive crashes into trees and rocks. After all, what goes up must come down. Next, the kite maker sews a piece of leather called a fitting onto the plastic strap. It's made of leather to protect the kite's structural joints, such as the nose of the kite. It gets a leather patch as well. The kite maker uses a serrated saw to cut the 10 carbon rods to size. They're 6 millimeters in diameter and range in length from 18 to 81.5 centimeters. They form the kite's skeleton, and like bones, they're the most likely part of the kite to break in an accident. But if they do break, it's easy to replace them. A variety of molded plastic, rubber, and aluminum fittings serve a dual purpose. They join the rods together and keep them from falling out of their sleeves. Now the kite maker attaches a nylon cord called a bridle to the fitting that joins the rods on the wing's leading edge. The bridle is the kite's rudder, steering the kite to the left or right. The bridle comes off easily if you need to replace the rods. The kite maker now attaches tension lines to 2 plastic components called arrows. They're located at the kite's wingtips. She ties elastic bungee cords through the arrows to hold the tension lines in place. This makes all the fabric parts taut enough to fly. Next, she attaches the bridle to the center rod, the spine of the kite. She inserts the rod into its protective leather pouch at the nose. She inserts other rods into both sides of the wing. These give the wing its curved aerodynamic shape and help the kite stay aloft. Finally, additional rods under the wing provide more structure and support. These rods spread the kite and help keep it open. In the mood for a sky-high experience? For $250, you can buy a handmade model like this one and go fly a kite.
When some innovative caveman invented the bow and arrow, it was a huge breakthrough. The discovery turned the Homo sapien into an efficient hunter-gatherer. These days, archery has made a comeback in the hunting community, and it's even been reclassified as an Olympic sport. So you could say the caveman's invention is still right on the mark. Today's bows are definitely not primitive devices. Crafted with calculated precision, they make it easier for you to take your best shot, and the caveman would have been very impressed. To make a longbow, a craftsman cuts 6 strips of cherry wood, a little more than ½ centimeter thick, using a bandsaw. Then with a belt sander, he repeatedly thins the wood strips on both sides, tapering the ends a little each time. The tapering gives the wood some flexibility, which the bow will need to launch arrows into the air. With his bandsaw, he now carves a handle from a piece of wood. Next, he brushes super adhesive glue onto fiberglass strips and the tapered strips of cherry wood. He works swiftly because the glue will start to dry in less than an hour. Now he layers the strips. The fiberglass strips buttress the 6 glued wood strips on either end. This process is called lamination. Next, he glues the wood handle to the fiberglass and wood lamination. And he tops it with a piece of masking tape to protect it from scratches and glue smudges during the next steps. Now the laminates get the squeeze. He places them on a curved plywood shape called a bow form. He positions a steel heat strip, a rubber hose, and another plywood form on top of the laminates. He clamps it all together, then inflates the rubber hose with an air compressor. The pressure from the hose combined with the heat from the metal strip mold the wood to the bow shape as the glue sets. 1 hour later, he removes the laminates, nicely pressed and glued into more bow-like curves. Now he draws the bow form onto the newly curved lamination, following a template made of fiberglass. With his bandsaw, he cuts the wood along the lines he's just drawn. He cuts an arrow shelf. That's the notch for the arrow to rest as the archer aims. Then he trims the handle, making it a little wider at the center for comfort. Next, using a coarse-toothed file, he hollows out little grooves in the upper and lower limbs of the bow. They're called string nocks, and the string will loop around them. To strengthen the tips, he glues little pieces of fiberglass and moose horn over them and the freshly filed nocks. He clamps it in a vice grip to set. When it's dry, he files through the horn and fiberglass to bring back the nock groove. He smooths it with sandpaper. Now he glues another piece of wood over the handle to improve the look and feel of it. He clamps it together while the glue dries, and 3 hours later, he sands it. Next, he wraps the handle in a piece of leather and stitches it together with nylon thread called artificial sinew. Many years ago, they used the tendons of an animal for thread. The leather will make the bow easier to grip. With a gel pen, he writes a serial number on the back of the bow, along with the draw weight. This bow will hold about 20 kilograms of pressure in check when it's drawn. This is a Flemish string jig, a wood fixture with posts on it. He loops nylon string around the posts. This is how he measures the string. It's always 4 inches shorter than the bow. He cuts it with a utility knife, then rolls wax onto it to make it easier to work with. He measures some string. Then he twists 16 strands of nylon, 8 black and 8 white, into a braid with loops on the ends. He hooks the string on the nocks, and it's time for target practice. As he bends the bow, energy is stored. He releases it, and the energy propels the pointed projectile. That apple didn't have a chance.